So we're looking at vectors. And vectors are, as it says here, a directed line segment which has two quantities that it is trying to represent. We're trying to represent a magnitude, which is going to be indicated by the length or the size of the vector, and then there's also a direction. So the way the vector is pointing, the way it's oriented, is another element of the information that's being communicated. So what we're talking about when we say a directed line segment is something that just looks like this. So we have an arrowhead, so here's the head of our vector up here, starting from the tail, so emanating from there. And so depending on how long I draw that vector, that's an indication of the magnitude. And then, of course, the way the vector is oriented is our direction. Unfortunately, as many different physics and math textbooks as there are is about the number of different types of notations there are for vectors. And so it really is something that we just have to be mindful of and be willing to adjust to. Some textbooks just use a bold lowercase letter to indicate you have a vector, but if I'm writing on the screen here, or if you're writing on paper, it's a little bit tough to tell whether it's bold or whether it's not to indicate it's a vector or just some variable. So for our purposes, I'm going to be using a lowercase letter with a arrowhead over the top of it to indicate that I'm trying to represent a vector of some sort. When we talk about just specifically the magnitude, so we're just concerned with the length of the vector, the magnitude of the vector, it will often be written in an absolute value like this. We'll also sometimes see it in a double absolute value written like this. It really just varies from textbook to textbook. So again, we just have to be malleable in this respect. When we talk about vectors being equal to each other or equivalent, that means that they have the same magnitude and the same direction, but they can begin and end in different places. So if we take the vector that I have sketched up here, and I have another one right here, as long as those two were the same direction and the same magnitude, they would be equivalent vectors, even though one is near the top of the screen and one is near the bottom. And then when we talk about vectors that are just indicating a position, so not necessarily like a velocity or acceleration or something like that, or a force, but instead are, if it's just trying to communicate a distance from one point to another, we'll say that that is a vector is in standard position if its beginning is at the origin. So again, just some terminology here for us to familiarize ourselves with. So in the first example here, we just want to find the magnitude and the direction of this vector. So even though I have these just to a single digit here, we'll treat these as integers and we'll just round our answers to the nearest 3 decimal places just to have some level of dimension to our answers. So in order to find the magnitude of that vector, so we're looking for the magnitude, remember the absolute value surrounding that, so I just need to find the length of that vector. And to find the length of that vector, I can go ahead and label up the side lengths of the triangle that I've created, and then just use a little Pythagorean theorem to help us solve. So 8 squared plus 5 squared, and I'm going to take the square root of that. So we're going to end up with the square root of 64 plus 25, or the square root of 89, which is 9.43. So there's the magnitude of this vector, so it's just the length. And then for the direction, we're going to be measuring the direction of a vector from the positive x-axis rotating counterclockwise, because we're certainly not going to be restricted to being in the first quadrant. So we have to be able to indicate a vector that's oriented up and to the right as being a first quadrant angle, versus, let's say, if this vector was reversed, to describe it with the exact same angle would be misleading about the orientation of that vector. So we're going to measure from the positive x-axis, rotating counterclockwise, as we usually do. And so to find that vector angle, the direction, I'm just going to use a little inverse tangent. So I can see that I've got the opposite side here and the adjacent side here. So if we set up a little inverse tangent of 5/8, and then if we just make sure that our calculator is in degree mode, we'll find that we have an angle of 32.0 degrees. And so again, we have to have both of these pieces of information to have the complete picture as to what's going on with this vector. What is it representing? We have to know its magnitude, we have to know its direction. In the second example, we can see our vector is oriented in the essentially opposite direction. We're going down and to the left instead of up and to the right. And we're also not oriented at the origin with our initial point, the tail of the vector, but we're instead out here at 6/8. And so the approach that I recommend taking for a circumstance like this is to just kind of create a temporary coordinate plane up at the tail of the vector, and then we can use that as the basis for setting up our triangle like we did on the previous question in order to be able to find the magnitude and then eventually the angle. So I'm going to drop a perpendicular here, and so we just need to label up the sides there. And I'm not going to pay attention to positives and negatives yet. That'll get resolved when I deal with the angle. So I just don't want to be distracted by those. So that horizontal distance there is 2. We're going from a coordinate of 6 to a coordinate of 4 in the x direction. And then likewise, the difference between the y coordinates is 6. So with that, we can find the magnitude of this vector by, again, applying the Pythagorean theorem to this triangle that we've created. So we've got a little 2 squared plus 6 squared. So we've got the square root of 4 plus 36. So we've got the square root of 40, which cleans up into 6.32 if we push buttons on our calculator. So there's our decimal point in there. There's our magnitude, and so now we need to figure out what that direction is. So I'm going to, first of all, recognize that that's the angle that I'm interested in. I need to rotate from the positive x-axis counterclockwise around to my vector. And so I'm going to have an angle that's between 180 and 270 degrees when I'm all said and done. But what I'm going to do is I'm going to find the measure of that angle that's right in there. So I'm going to use this reference angle as kind of my, let's get that correct. So I'm going to use that reference angle as my, the angle I'm going to calculate for, and then I'm going to adjust to reflect the fact that I have to rotate that extra 180 degrees to get to there. So we can again find the reference angle using a little inverse tangent. So inverse tangent of opposite over adjacent, so it's going to be of 6/2. And so if we calculate that, we end up with an answer of 71.6 degrees. But again, that's not the direction of our vector. We need to make sure that we adjust for the fact that we've rotated this extra 180 degrees on top of that 71.6 that we just solved for. So we've got to add 180 plus 71.6 to get our true direction for this vector to indicate that we're going down and to the left. And so that's going to be 251.6 degrees. So again, just have to make sure that by some mechanism we adjust for the fact that that angle that we solved for isn't the angle for our vector. It's instead all the way from the positive x-axis that we want to find it. But in both cases, it's essential that we have both of these pieces of information, because if we only have one or the other, we're not communicating the full picture as to what that vector is trying to represent.